So today's topic is multi-stage differential amplifier. And so far we have discussed the differential amplifier, that is, you can also call the single stage. And we have learned how to analyze, how to determine the different parameters of the differential amplifier, like the gain, the input, output resistances. So multi-stage, first, why we need multi-stage? Because as we have discussed for our conventional amplifier, single stage conventional amplifier, the common emitter, common collector, common base, it is difficult to satisfy all the requirements of a good amplifier with a single stage amplifier. So that's why we go for multi-stage amplifier. Like if you take, for example, the two parameters, two most important parameters of the amplifier. One is the gain, what we call the voltage gain. The other is the input resistance, in this case RIT. So voltage gain for the differential amplifier is written as the AD. Right? So if you are taking the output for S from a single node, in this case it will be, if you are taking output from VC2, so we write VC2 by VIT, and that will be this positive half GM RC. Right? And GM is, what is our GM? And GM is IC by VT. Right? GM is IC by VT, and IC is alpha IE. That is we write alpha IE by VT. Now, in this case, what is IE? IE is the current that is flowing in the emitter. So IE will be here, and IC is here. So these are, we are showing only the DC currents, not the small signal currents, but both will be here. But since we are analyzing for the GM, which depends on the DC collector current. So now IE, which is our emitter current, what we can see here that IE is the I by 2. And I is the current of this current source, and we assume that this is known. So from this current, we can determine IE, which is half of this I, and then we can determine IC, which is alpha IE. So this becomes alpha I by 2 VT. Right? So that is how we can determine the GM. GM depends on this current, and yeah, that will depend on the and the gain, and that will determine the gain. So now half GM, if you substitute here, then we get alpha I and RC divided by 4 VT. So that is how the gain expression will be using our known parameters, the current of the current source, the RC, and so that will determine the gain. Now RID is, we have there is 2R pi, and which also we can write as 2 beta plus 1 RE, right? And we have we know the current, and this, so that is RE is VT by I. Okay. Now IE, we have determined this. This is our IT substitute for this. So this will become we have I by 2, so 4 beta plus 1 VT by I. Right.
Sir,
Yes.
we couldn't see properly on the right side.
Okay. Right side is cutting off.
We could only see 4 beta plus. That's it.
Okay. Okay, so this is Okay, so what we have derived here, the gain expression is alpha I RC divided by 4VT. And we have determined the RIT, which is 4 beta plus 1 VT divided by I. Can you see this?
Yes, sir.
Okay. So now you see that these two are gain and the input resistance are mutually, I mean, they are conflicting, right? We want both high gain, we want high gain, and also we want high input resistance, right? But they are mutually conflicting because to increase the input resistance, what we need to do, we have only one variable here, that is this current I. This is the bias current I. So this is the only variable, and we can work with this variable. We can vary this I, and we can vary both the gain and the. Here we have another variable, that is RC, right? So, but for input resistance, we have only one variable, that is current I. And what happens if we reduce this current I to increase RID, right? We want to reduce the current I so that you can have high input resistance. And when you reduce this current I, what happens? With the reduction of current I, your gain will fall, right? Gain goes down. So when you want to increase one parameter, the other affects in a different way. If you want to increase the gain, so you want to increase I, that will reduce your input resistance. Increasing the gain also we can achieve by RC, so that is another variable. So what we can do, we can reduce the current I, increase RIT, and we can try to increase RC. But that is limited. I mean, to some extent we can do that, not too much. The other way of increasing the input resistance, there is another way. One is decreasing the bias current, that increases the emitter resistance RE, R pi, and RIT. So that is one way to increase the input resistance. The other way to increase the input resistance, that if you add a resistance in the emitter, right? If you add a resistance in the emitter, R. So if we add the emitter resistance, then what happens? Then okay. So increasing the emitter, introducing the resistance in the emitter circuit will also increase your input resistance. So what will be the input resistance in this case? In this case, input resistance RIT will be 2R pi plus 2 beta plus 1 R, right? So now here, the input resistance will go up because we have another component RE, and that is multiplied by beta plus 1. So we can use both a reduced current I to have high R pi, and also into from the RE, we can have another component added to the input resistance. So this will significantly increase our input resistance. But what about the gain? Right? Will it have any effect on the gain?
So the term RE will come on the denominator.
Right. So if you have this now, what happens that so now gain expression, it will become something like this. You have RC resistance in the collector divided by the resistance in the emitter. So there's 2 times small RE plus capital RE. So with the introduction of the emitter resistance, the RID, while RID goes up, the gain again goes down. Right? So any attempt to increase the input resistance actually affects the gain. In an adverse way, it decreases the gain. Any attempt to increase the input resistance will reduce your gain of the amplifier. So that is why these two are mutually conflicting requirements to having high input resistance at the same time high gain of the amplifier. So it is difficult to achieve both the requirements in one single stage. So then what we do, we go for a multi-stage amplifier where we have the first stage we design to have high input resistance, and the second stage, or we have a number of other stages, they are designed to have high gain. So now here is our multi-stage differential amplifier. Now the connection you have to take note of how it is connected. The VC2, the output, this is connected to the first transistor here Q3, because in differential amplifier this side we get a positive voltage, this side we get a negative voltage, right? So this VC2 is connected to the first one here, because we apply the voltage like this, positive on this side, negative on this side. And VC1 goes to the input of Q4, right? So this is how the output of the first transistor will go to the input of the second transistor. Okay. So the output here, this is our VOD, the differential output of the first. This is how it will go to the input, right? So VOD will be here, right? This plus, okay, this plus and this minus. And so this one here, this is our input stage, the input stage, and this is supposed to provide high input resistance RID, right? And these are output states, and this is supposed to provide high gain. And to increase the input resistance, what we do, well, we can take the bias current I, the low bias current, and we also incorporated an resistance in the emitter RE. So these two we can do to enhance the input resistance here. The other one, the second case, we need high gain. So in this case, the bias current I2 should be high, so that we get high GM and high gain. So this is the strategy that you can use to achieve both the high gain and the high input resistance. Now, what will be the overall gain of this amplifier? The overall gain is, we write as V0 by VID. V0 by VID. So now this V0 by VID, this overall gain, we can express as the product of two gains. One is V0 by VOD, and then V0 by, VOD by VID. So the first part here, that is actually the gain of the first output stage. So we can write as a differential gain for the second stage, and that is the differential gain for the first stage. Now this gain here, the output stage, we are taking output from a single node. So this one, the gain expression will be half GM2, GM2 and RC2. And for the this one, for the first stage, the AD1, the differential gain, we are taking the output differentially, not a single node. And we also have a resistance in the emitter. So the gain will be the resistance in the collector divided by the resistance in the emitter. So that formula, it will follow. And that we can write. But in this case, what's the resistance in the collector? Right? So that is one thing we have to pay attention here. See, we have the resistance RC1, but that is not the only resistance in the collector, because the output of this one is connected to the input of the second stage, and the second stage will have a certain input resistance that we can show like this. It is RID, RID2. Let's say these are RID1, or these are RID. So input resistance of the second stage. Now that input resistance, right, will appear like a load resistance here, right? Will be like a load resistance for the first stage. So something like this, you have a load resistance that is RID2. Right? So this input resistance for the second stage will be like a load resistance for the first stage. So the actual resistance in the collector, the effective resistance for the first stage. So what will be that resistance for the first stage? We discussed in the last class. Do you remember? Hello. Can anyone remember what will be the effective resistance?
Sir, forgot, sir.
That will be the half of the load resistance. So that will come in parallel with RC1, in this case RID, 2 divided by 2. So half of this load resistance will be in parallel with RC1, and that will be effective load resistance. Now, what is RID2? Right? What's the input resistance here?
The 2R by 2.
Right, you can write 2R by 2, the R the base 2 emitter resistance for the second stage. So if you take R half of this, so we get RC1 in parallel with R by 2. Right? So that will be our effective collector resistance in the first stage. Now, so the overall gain will take this form. We have collector resistance RC1 in parallel with R by 2, and that will get divided by, and the small re, we write re1 plus capital R. So that will be the overall gain for the multi-stage differential amplifier, and we have already shown what is RID1. So any question, guys?
No, sir. So this is RE1 plus
Sorry,
in the denominator RE1 plus.
so you can't see this part?
No, sir.
Why is that? Okay, shifting.
RE1 plus RE or 2RE, sir.
RE1 plus capital RE.
Capital R. Okay, sir.
Let me write it here. There's so much space here, but you can't see it. Don't know why. So AD2 is half GM2 RC2, and AD1 is RC1 in parallel with R by 2. Then the RD1 plus R. So now you can see, right?
Yes, sir.
There's so much space left here, but I don't know why it's not visible. So now we'll take a numerical example and see how the different parameters affect the circuit output. Sometime. So we assign some numerical values here. Let's say this is 0.5. This one, 2. This is 400. RC, 20K. Okay. So we are taking the output here from the single node or collector of Q4, and that is our input resistance RID1. So you see that we have taken I 1.5 milliampere and now I have taken I2 2 milliampere. So that is so that we have high input resistance, high value for the emitter, the arc by this resistance, and that will contribute to high input resistance. And we have taken bit higher value for I2, 2 milliampere, so that it gives us high gain. Okay. So now we have this gain, differential gain, overall differential gain is okay. So maybe first we determine the RID, the input resistance. RID1 will be 2R phi 1 plus 2 beta plus 1 RE. Right? So in order to determine the input resistance, we need to determine R pi, which is beta plus 1 RE. Right? Now what is RE? So first RE is Vt by IE. Right? And that we can write as 2 Vt by I1. So in this case, I1 is 0.5 milliampere. So here we get 2 and 0.5 milliampere times Vt. Now what is Vt? Vt is the thermal voltage. So we assume a convenient value, let's say Vt is 25 millivolt, right? So to be exact, it is around 26, but that's a convenient value for calculation. 25 millivolts, so yeah, that's, we keep it as it is. So we have milliampere, millivolt cancel out. So 2 times 25 millivolt, and there you have 0.5 milliampere. So if you do the calculation, what do you get?
100
It's
ohm.
50, 100, right?
Yes, sir.
So it will be about 100 ohm. So that will be small RE. So then we can calculate the R pi, which is beta plus 1 RE. Now beta assuming to be 100, so we can take 101 times 100 ohm, and that will give us 100. It's about 10 kilo ohm, right? 10.1 kilo ohm. So that we can take as just 10 kilo or yeah. So now this is 2 times, let's keep it as it is, kilo ohm, 10.1 kilo ohm, and that plus 2 times beta plus 1 is 101. And the 400 ohm, if you convert into kilo ohm, so you get 0.4 K. That is in kilo ohm, right? So now if you do the calculation, what do you get? This will be your 100, 40.4, 42, 82.
Sir, 101.
Just 101 or you have something more?
No, no, sir, just 101.
Okay, so we get about 100 kilo ohm of input resistance, which is not bad, right? 100 kilo ohms of input resistance. Now, what's the gain that we can get here is the first we have that we wrote in the previous. The gain is the product of the gain of the two stages, that 82 and 81. And 82 we had half, that is what we had, right? Half GM1, sorry, GM2 and RC2. Okay, let's get back to the previous one. We can just write the, oh no, that's not the one. Yes. So gain expression, okay, we wrote like this. Okay, that's okay. Okay, so that is how we wrote, and the first case was the effective RID2, so that is RID2 by 2, and then we have small RE, and then this one RE, right? So that is the gain for, and then GM2 was IC2 by VT. IC2 is half of this, so that we can write as I2 by 2 VT. Okay? So we are assuming alpha is 1. So in this case, just approximation. So then this we write as 1 by 4. So I2 RC2 divided by 4 VT. And this one is RID2 is 2R pi, 2R pi 2. So we get RC1 and R pi 2, and we have RE1 plus R. So the differential gain for the second stage, I2 is 2 milliampere, RC2 is given 3, and that divided by, we have 4 times VT in, we have 25 in volt, we get 0.025, right? Millivolt converted into volt. So you get 6 and divided by 0.1, right? Give you 60. So that will be gain for the second stage. And the gain for the first stage, AD1, will be, we have RC1 is 20K. So 20 times R pi 2. Now, how much is R pi 2? Right? R pi 2, again, you can write beta plus 1 RE2. And we have beta plus 1 RE is Vt by IE, IE2. Now here we have beta plus 1 is, okay, so we have beta plus 1 and IE is half of I2, so we get 2 Vt by I2. So that is our final expression, and here substituting the values, assuming beta to be 100, we get 2 times Vt is 0.25, right? Vt will be, if you convert into volt, 0.25, and I2 in milliampere is 2 milliampere. Okay. So this one, if you do the calculation, 2 and 2 cancels out, we have this times about 100, so about 2.5K. So that will be our R by 2 about, and that will be 2.5K. So here you have 20K, and that will be in parallel with, sorry, 20K, and that will be in parallel with 2.5K, and that we divide by this RE, small RE plus capital RE. Small RE was 100 ohm, do you remember? This is, I think, 100 ohm. And capital RE is 400 ohm. So if you convert into this kilo, so it will give 0.5, to that it will be 0.5K. So if you do the calculation, how much it is?
So 4.44.
4.4. Okay. So the gain for the first stage is 4.4. So these are the gain for the 2 stages. So now we can determine, can calculate the overall gain. So that is 60, that is 4.4, and that is 24. 4 times 26. Right? So that will be the overall gain. Any question? See, the gain of the first stage was quite small, so only 4.4. In order to achieve the high input resistance, we have achieved an input resistance of 100 kilo ohms, and we end up with a gain of only 4.4. So now we see another aspect of this differential amplifier. That is the DC analysis. DC analysis is important for any amplifier in order to ensure that your amplifier works in the active region and for the whole range of your input signal. Amplifier will be able to amplify while it stays in the active mode. Now, how to ensure that, right? So one thing that we like to point out here. Okay. So the gain of the first stage, AD1, was what we found out is RC. RC1, that was in parallel with R pi 2, and that divided by small RE and capital R. And the gain of the second stage, AD2, was half GM2 RC2, and which we wrote as GM2 is IC by VT, that is I2 by VT. So we wrote as I2 divided by, okay, I2 RC2 divided by 4 VT. So that is how we express the differential gain for the second stage. So you see that if you want to increase the gain, what are the parameters, right? You either increase the I2, the current, the bias current here, either increase this, or you increase RC, right? Or you increase this RC. So whichever you increase, overall what you do, right, you are actually increasing IC, RC to this voltage drop, right? So if you want to increase this gain for the second, is actually what you are doing, you are increasing the IC, this voltage drop, this part of the current is flowing through this, and basically you are increasing this voltage drop, right? That is this is the voltage drop IC2 RC2, right? And IC2 is half of I2, right? So basically you are increasing the gain. And the higher is this voltage drop, the higher is the gain, right? But you cannot increase this voltage drop indefinitely. You cannot increase RC2 indefinitely, or you cannot increase IC2 indefinitely. There is a limit, because this is a DC voltage drop, and you have the DC supply here, right? So for higher voltage drop, you will need higher supply. That is one constraint. So high voltage drop, high gain means high voltage drop, and high voltage drop means you need a high supply voltage. But there's a constraint to that. The other constraint is the collector voltage VC4. Right? Now, in order for the transistor to remain in active mode, you see that the collector base junction has to remain reverse biased. Base emitter junction, while it has to remain forward biased, the collector base junction has to remain forward biased, and for this is an NPN transistor. Right? So VC4 has to be greater than VB4, right? So that you have to ensure that this voltage drop remains greater than the VB4. And if you have a higher voltage drop here, so what happens that VC4 is given by VCC minus RC2 RC2. Right? So if you increase this voltage drop here, so this one will reduce, right? The higher is this voltage drop, the lower will be your this voltage, and chances are there if you take too high value for this, it the VC4 it may go down below VB4, and then transistor will enter into saturation, right? It will not work as an amplifier anymore, right? So there is a limit. So this VC4 has to be a VC4, which is VCC minus IC2 RC2, has to be has to remain greater than VB4, right? So that means your IC2 RC2, it has to remain less than, if you change this VCC minus VB4. So that sets the limit for how high you can go, right, for this parameter. Also sets the limit how high you can set the gain of this amplifier, right? So because the denominator is a constant, right, which is about 0.1 volt or 100 millivolt. Right? So this sets the upper limit that you can have for the gain of the amplifier. Now, if you look at this circuit here, now how high you can go for this one, or what are the constraints, limits, right, you have. So first we start from this circuit here. So I1 is 0.5. So that from that we can easily determine the currents here, right? So the half of this I1 will go here, half of it will go here. So if alpha about 0.5, you can say this is about 0.25 milliampere, and this also 0.25 milliampere, right? So with this, we can easily determine the collector voltage here, VC2, how much will be VC2, right? VC2 will be in the VCC, which is 15, and that minus this IC1, RC1. IC1 is 0.25 milliampere, and that times RC1 is 20K. Yeah. So if we do the calculation here, that 15 minus this is 20K, that is about 5, right? So it comes down to 10 volt. So VC2, both this will be same, both this one will be same voltage, because current is same, everything same. So VC2 we get 10 volt, and VC1 that will be same as VC1, also 10 volt. So both at this Q3 and Q4 bases, the voltage will be 10 volt. So we get a 10 volt of DC voltage, which is quite high at the input of these two transistors. So VC4 has to be greater than 10 volt. So VC4 is what we can conclude, that VC4 has to be larger than 10 volt. It cannot be lower than 10 volt. Is that clear? Now, how large it has to be? I mean, how high, how much higher it has to be from 10 volt, right? If you want a high gain, right? So the higher you want the gain to be, the lower will be VC4. Right? So like our example, the gain that we calculated was 262, right? That's the overall gain, but that's overall around the gain for the second stage was 60, right? It was 60. So if you have a gain of 60, okay, so the example that we took here, the 2 milliampere and RC was 3K, right? So in this case, the ICRC drop was, we had 2 milliampere, so 1 comes here, 1 milliampere, RC is 3K, so that gives us 3 volt of drop, right? We get a 3 volt of drop here. So 15 minus 3, then we get VC4 is 15 minus 3, and that gives us 12 volt. Right? So what we have here, that VC4 is 12, and VB4 is 10. So we have a margin of 2 volt, right? Voltage difference. So VC4 is 2 volt higher than the VB4. So this will keep our this transistor for the second stage also in the collector base junction reverse biased and keep it in the active mode, right? Okay. So let's show it in a let's show these different voltages in a plot so we can better understand the relationships among the different voltages. So let's say this is our voltage. We are showing the voltage and volt, and so let's say this is our collector voltage VCC, right? Which is, we have 15 volt collector voltage. It's constant 15 volt. This is our time axis, and then we have our VB, the VB4, which is about 10 volt, right? Somewhere here, let's say we have VB. So that's our VB4. VB4 is 10 volt, right? Then we have VC4, which is 12 volt. So that will come somewhere here. So this is our VC4. Right? VC4 is 12 volt. So here you see that VB4 is in VC, the collector voltage is at a higher voltage than the base voltage. So the transistor will remain reverse biased. And this is the voltage we have, right? And what is this voltage drop? This is the voltage drop across the collector resistance. So that is your IC2, RC2, okay, which is 3 volt. So that's the voltage drop in the collector resistance. If we would like to draw this for your convenience. So we have something like this. Okay, maybe that is not. So that is how our circuit was. It is our Q3 and Q4 second stage. And here we had the IC2, RC2. So that is the voltage drop. The current flowing here is our IC2. So that is the IC2, RC2 voltage drop. And then from VCC, you have this drop, and then you have this VC4. And then you have this voltage here, the collector base junction voltage, reverse bias voltage VCB, right? So there's the voltage VCB here, right? And then you have this VB4, which is at 10 volt. VB4 is at 10 volt, VC4 is at 12 volt, and then you have this 15 volt. So this will work perfectly fine, no problem. Now let's take for example the here we have considering only the DC voltages, and we're trying to see if everything is in right order, if it will work fine. Now, if we have the AC signal superimposed on this, so how that will affect? Now, let's say we have an input voltage VID about 10 millivolt, right? VID about 10 millivolt. Now, that was our input signal at the input of the first stage. The overall gain we have calculated about 262. So the output voltage V naught will be the actual input voltage times the overall gain, and that will be 10 times 262. So that will be 2060 to 620. This will be in millivolt. Convert into volt, that will be 2.6 volt, right? 2.6 volt. Now, this depends if it is peak to peak or peak voltage, right? Let's say this is our peak voltage. Peak value of the input voltage is 10 millivolt. So if that is their peak voltage, then this will be also our peak value of the output voltage, peak value, right? So output will be something like this. Right? So with the peak value of 2.6 volt and a minus 2.6 volt, right? So that is how the output will vary. It will be a 2.6 plus minus. Now we have VC4 here, Now, on top of this, now we will have the signal voltage, 2 VC4 is our DC bias voltage. And on top of this, superimposed will be this AC signal voltage with a peak magnitude of this the 2.6. So output voltage will have basically have a DC voltage VC4 and then AC signal voltage of the 2.6 peak value. So this is fixed at 12 volt and superimposed on this is peak value of 2.6 AC signal voltage. So how it will show in this diagram. So you have this 12 volt VC4 and on top of this you have another AC signal voltage with a magnitude of 2.6. Let's say 2.6 is somewhere here, which is below 3 volt, right? We have a difference of 3 volt here. And this is 2, so 2.6 come down somewhere here below 10, something like this. So then this will go so like something like this, right? So this is didn't come in right proportion because this part is showing to be the higher magnitude. The margin is greater here. So something it will be something like this. Maybe should little bit put it little bit at a lower position. But the main concept here, what we see that now this one, the what is fluctuating, right? So this is our actual collector voltage, the total collector voltage VC4 or V0. The total collector voltage and the collector for VC4 is the summation of the AC and the summation of the summation of the DC and the AC signal voltage. DC pass voltage, AC signal voltage, and which is fluctuating with time because of the AC signal. And what you see, the maximum value of this, the collector voltage VC max is 12 plus 12 plus 2.6, which is 14.6 volt. And the VC4 minimum value will be 12 minus 2.6, which will be 9.4 volt. Now what we see here, VC max, this is less than VCC, which is 15 volt, right? So that is fine. But in this case, VC minimum value is lower than VC4, VB4, which is 10 volt, right? So this collector voltage at some point, right, of time, this goes below the base voltage of the Q4. So is that okay, or will be there any problem because of this?
A problem in biasing.
What problem? What problem we'll have?
We'll go on cutoff region.
Not cut off. You see that what happens at some point of time, the collector voltage goes below the base voltage, and when it goes below the base voltage, so for this part, right, the Q4 will become the collector base junction, right? Collector base junction will become forward biased, right? For this period of time, this interval of time, the collector base junction of Q4 will become forward bias. And when it does, right, when it becomes forward bias, what happens? What will happen during that time?
So VCC is greater than VB4 or VC is less than VB4.
You can't see the diagram here.
Yes, sir.
So what happens during this period when you see this time interval?
Yes, sir.
What do you see? Is it greater or lower?
Lower.
Lower. So what happens if it gets lower than VB4?
Yes, sir.
So what happens?
Forward bias.
It becomes forward bias. And if it becomes forward bias, then what do you get? If the collector base junction becomes forward bias, what happens to Q4? Will it remain in active mode?
Yes, sir.
Yes. What is the condition for trans to be in
Oh,
active?
sorry, sir. Yeah, it should be reverse biased.
It should be reverse bias. So,
Yes, sir. Both of them are in forward biased condition, so in saturation.
right. So the Q4 will enter into saturation, right? The Q4 enters into saturation. So the transistor during this time interval, it doesn't stay in the active mode, it enters into saturation. And the moment it tries to cross this, right, VB4, so it leaves the active mode and it will not work as an amplifier, right? So at the output, you will not get something like this. Maybe you get something distorted, right? You get some because it is not in active mode. Maybe something like this. No problem. Okay. So this during this time interval, it leaves the active mode. It doesn't work as an amplifier. So with the 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 circuit that we have with the different parameters and the values of the different parameters as said, the RC1, RC2, the I1, I2, right? We have the margin here. We have this margin of how much? 2 volt, right? And here we have 3 volt. So this margin actually determines what is the maximum window we have, right, for the signal to swing, right? So this ICRC drop that is we have in across this resistance, so that will give the margin of the positive swing of the signal, right? The positive swing, how much margin we have for the positive swing. And this voltage here, VCB, determines how much margin we have for the negative swing. So this is in the ICRC resistance voltage drop, and this is in the collector base junction, right? And of course, for any output, we want the symmetric, right? The the equal amount of swing in both the directions. Otherwise, signal will be distorted, right? So we want equal amount of swing. So the margin that we have, the lower one will determine the maximum swing that we can have for the output signal. In this case, the lower one, we have the 2 volt for VCB, and the ICRC is a little bit greater, that is 3 volt. So this VCB voltage 2 volt will determine the maximum swing for the signal that we can have, and that is 2 volt. But if we have an input voltage 10 volt and our signal where gain is 262, So that comes out that our signal swing has to be 2.6 volt, and that our amplifier is not able to provide that much signal swing. It can provide only maximum 2 volt of signal swing. So that is not enough, right? So we'll not be able to get this output, we'll get something distorted. Maximum signal swing we can have for this, our circuit is 2 volt. So maximum gain also, you can see that if your circuit designed like this, and you have 2 volt of maximum signal swing, and your input voltage is 10 millivolt, that is 0.01 volt, so you can have maximum gain of 200, right, volt of maximum gain. So if you want to accommodate this signal of 2.6 volt, so this difference, the VCB, you have to increase to at least 2.6 or greater than this, right? So let's say we want to accommodate this signal. We want to have an output signal that has a maximum swing of at least 2.6 or greater. So we have VC, IC, RC3. Then we also should have a 3 volt of difference here, right? If you can set VCB at 3 volt, the collector base voltage 3 volt, then signal will be able to swing in both directions, right? 2.6 volt. It will be able to swing maximum 3 volt, and of course 2.6 is also within that limit. So how do we do that, right? So in order to do that, now VB4 is set as 10 volt. So you need to reduce that to 9 volt, right? If you reduce that voltage, the bias voltage coming at the base of VB, the Q4, if we reduce that by 1 more voltage, then you can increase the, the reverse bias, the voltage here by 1 volt, it will be 3 volt then, and you can accommodate that voltage. Did you get that?
Yes, sir.
This is an important concept when you want to design the amplifier for a particular signal to amplify. So these are the things, right, factors you need to consider, and these will affect your output if you don't have the proper biasing set properly. If they cannot accommodate the different the magnitudes of this your output signal, you won't get the output even everything is correct, right? So it's not just the gain, also biasing has to be done appropriately so that it can accommodate, right, the signal, right, without going into saturation or cutoff. So we need to reduce this voltage here, right? And how we can do that? Here the voltage drop ICRC, I mean, you need to reduce from 10 to 9. So if you want to reduce the voltage here, that means you want to increase the voltage drop here, right? And that you can do by 2 ways. One is by increasing the resistance RC, or you can do by increasing the current, this current bus current IC. But if you don't want to, if you increase the bias current, that will reduce the resistance. So if you don't want to reduce the resistance, input resistance, so what you do, you just increase the RC drop, right? So so what you do, you have to increase by 1 volt. So right now it is 5 volts. So if you want to increase 20k, you have 20k times IC, and that should be difference should be 6 volt. So that should be 6. So from that you can calculate how much your IC should be. That should be 6 divided by 20. Right. So that should be 0.3. No, we are trying to determine the RC. So RC is fixed at 0.25, and that should be RC. So from that we can calculate how much should be our RC. RC should be 6 divided by 0.25. Okay. Is that correct? And that will give you how much?
24.
So 24K. Right? So now, if you increase the RC value here from 20 to 24K, then you will have a voltage drop of 6 volt. Before it was 5 volt. Now the voltage drop will increase by 1 volt, and the voltage here will be 9 volt, and that will this now the voltage at both the ends will be 9 volt. Now you will have a voltage drop here 3 volt, and also a voltage drop here 3 volt, and signal will be able to swing in both directions by at least 3 volt, and the circuit will be able to accommodate that output, right, of 2.6 volt. And you see that we have taken a input voltage, an input voltage of 10 millivolt. So, but we can have an input voltage of a maximum 20 millivolt for differential amplifier because of the two transistors. And if the input is your 20 millivolt, then you see output will be even double, right? Now we are having 2.6, and that will multiply by 4. So it will be even more than 5 volt. So uh, if input maximum input is 10 millivolt, then this circuit will work. This circuit will work fine. But if the input is even higher, then this will again fail, right? So overall, these things you need to consider how much maximum output you want, right? What will be the maximum value of the output voltage? What is the input voltage? That will determine the gain. And then if this is your maximum output voltage, and what should be your biasing currents and the voltage drop, so that your the amplifier can accommodate that output signal swing. Right? Is that clear, guys?
Yes, sir.
So we discussed, addressed the issue of this biasing in this differential amplifier. So we just consider one factor, the one aspect of the biasing, that's the voltage. There's another factor, that is the current, right? And what sets the upper limit of the current, that will be that will depend on the load resistance, how much current your amplifier has to supply. So and how much maximum load current that amplifier needs to supply, that will determine the maximum value of the bias current. Your bias current should be such that it is able to supply the load current. Right? So if your bias current is lower than the load current that is needed, then again your amplifier will fail. Right? It will not work from the whole range. Right? It will go into cutoff. Right? If it doesn't, if it is not able to supply that maximum amount of current. So that also has to be considered while you are designing your amplifier. So that's the voltage also you need to consider the current, right? So if the current is large enough to supply the current that is needed by the load. So more will be discussing in our next class of this differential, the multi-stage differential amplifier, because here the output, you are taking the output directly from the collector in integrated circuit. We don't use coupling capacitor, because coupling capacitors are bulky. So now here in the output we have both the AC and DC, but in the output we want only the AC signal, not the DC signal or the small signal. So how we can get rid of the DC signal? DC high, this is very quite high. Yes, we have at the collector. So how we can get rid of this DC voltage coming to the load? So that we'll discuss in our next lecture.